So we're going to be doing the Module 3 vocabulary. So if I'm going to start off, we're doing relation, a set of ordered pairs to compare the domain and range. Notice that it has the braces on both sides. You need to use that. And then it has 4 ordered pairs. Okay, the domain, the set of all possible input values or x values for a given function. From the relation that was up above, all I did was put all the x values and I put them in numerical order. Range, the set of all possible output values or y values for a given function. And I still use the same relation at the top. Okay, and 4, if you notice 4 was in the first and the last ordered pair, I don't need to write it twice, just once. Okay, mapping. It illustrates the relationship between the domain and range by showing how each element of the domain is paired with the elements in the range. Usually there are 2 circles or 2 boxes on each side. It has the domain, it has the range, and arrows that show from what domain value to what range value it's going. Independent variable. The values in the domain, or x values, correspond to the independent variable. It is subject to choice. Dependent, the values in the range, or y values, and they correspond to dependent variable. Scale. Okay, when graphing on the coordinate system, the scale of a graph refers to the distance or the interval between tick marks on the x and y axes. If I look at this, the x's are going up by 1s, the y's are going up by 5s. If I look at this one, again, the x's are going up by 1, but the y's are going up by 50. I picked all ones that have going up by 1 on the on the x. It doesn't always happen like that, just in these examples that I have, and these are going up by 2s. A function, a relationship between the input and output, that there is exactly one output for each input. If I look at this, another way to tell is, does the x value ever repeat itself? No. Does the x repeat itself? No. The x wouldn't repeat itself here either. Okay, vertical line test. Draw invisible vertical lines through the graph. If you only hit one point at a time, then it's a function. So I have this graph, draw a bunch of vertical lines, and you wouldn't actually draw the lines. Okay, it only hits it at one point at a time, so that is a function. This right here, immediately, if I put a line through, I'm going to hit 2 points, so that means it's not a function. Okay, function notation. It's another way to write an equation. All you're doing is replacing the y with f of x. And the reason we're going to do that is, if I have f of x, I'm going to know what value I'm plugging in for x. So it could be f of x, but it could also be g of x, h of x, l of x. It could be any letter except for x and y, telling what the name of the function is. Discrete functions, points that are not connected. If you look at this, none of these points are connected. Continuous function, points that are connected to form a curve or a line. Okay. Neither discrete nor continuous function. Some points are connected by a line or curve, but it's not continuous everywhere. So it's continuous on this side, it's continuous on this side, but not in between. So this is neither. A linear function. Guys, it has to be a line. In order for it to be a function, it can't be a vertical line. Vertical lines are when x equals a number. So make sure that you understand that a line has to have an exponent of 1 for the x and y. A linear equation, Just has to be able to form y equals mx plus b or ax plus by equals c. Nonlinear function. It's in the name. It's not linear. It doesn't make a line. It will never make a line. So if it's not a line, then it won't have a constant rate of change. So that is an absolute value. It doesn't have a constant rate of change. This is a quadratic, or the picture is a parabola, but it's a quadratic. This is a cubic function. Okay, they're functions, all of them are functions, but they don't make a straight line. X-intercept, the coordinate of a point that crosses over the x-axis. Okay, so I have this graph. This is a x-intercept, that's an x-intercept, and that's an x-intercept. Y, the coordinate of a point where the graph crosses the y-axis. So on this one, 0 is going to be the y value. That's the only place it hits the y-axis. Positive function. Okay, first of all, it's a function. When it's a graph, when its graph lies above the x-axis. So the part that's above the x-axis is the positive function. The part that's below is the negative part of the function. Okay, line of symmetry. It cuts the graph in half. Each side of the line has the same characteristics. It does not have to be the x or y axes. Now, I happen to have examples of this being the y-axis, but right here, look, it's not the y-axis here. It's next to the y-axis, but it is not the y-axis. Okay, next, increasing. When the graph goes up from left to right, that's super important. As the x value gets bigger, so do the y values. So if I look at this, the x values get bigger from left to right, and the y values here are getting higher and higher. So this part right here is the increasing part. Decreasing, the graph goes down from left to right. So as the x values get bigger, the y values get smaller. So here and here. If you look at this point right here, negative 4 and positive 6. I don't know. But if I come down here, this is going to be negative 2, negative 3. I don't know. But as the x got bigger, the y got smaller. Extrema. Points that are the location of relatively high or low values. Okay, so a relative maximum, a point on a function's graph where the y coordinate is larger than all other nearby coordinates. So if I look at this, yes, this goes higher up, but it's called a relative maximum because all the other ones that are around it, those numbers are smaller, okay? Look how high this y coordinate is. Okay, none of the rest of them around it are as high as that. Okay, relative minimum does the same thing, but it's at the minimum. Okay, a point on a function's graph where the y coordinate is smaller than all other nearby. Okay, so yes, this keeps going down, but right around this, that's why it's called relative, because, oh, sorry, I was still explaining, because it's not going to be the absolute minimum because this keeps on going down. This isn't going to be the maximum because this keeps going up. It's a relative maximum and a relative minimum. So in behavior, describes the values of a function at the positive and negative extremes of the domain. So as I'm coming out here left, as I'm getting further and further away from the origin, the x's are getting smaller and smaller and smaller and smaller. The y's, though, are going up and up and up and up. Okay, so the y's are increasing. Okay, so it's increasing on this side. if I'm going down here, my x's are getting bigger and bigger and bigger and bigger. What are my y's doing? They're getting smaller and smaller and smaller and smaller. Okay.